Hey everybody, it's Monday, March 15th, and as you can see here in the aim today, our goal for today's video is to pick back up right where we left off on Friday. So if you remember on Friday, I asked you to solve a series of questions on the rotational motion, torque, and rotational dynamics problem set. In the last video, we covered 1 through 5, and so to start this video off for today, we're just going to finish up 6 and 7. And so we'll start with number 6. This one in the Tipper's book is B6QRT05, pulleys with different radii, rotation, and torque. This one says here, a wheel is composed of two pulleys with different radii labeled A and B that are attached to one another so they rotate together. Each pulley has a string wrapped around it with a weight hanging from it as shown. The pulleys rotate about a horizontal axis at the center. When the wheel is released, it is found to have an angular acceleration that is directed out of the page or counterclockwise. And you can see this whole thing shown here in that picture on the right. The question says, is the wheel going to rotate clockwise, counterclockwise, or none? I guess that means not at all. Explain your reasoning. I want you to take a second to read the description one more time. Take a look at that diagram and think about the reasoning. When you hit play, we'll go over it. I think this question is a pretty good example of a kind of question that you might see on the AP test, where you really want to make sure you look at all of the parts before you answer the question. Because just to be totally honest with you, when I first made the answer key for this question 7 years ago when I was first teaching this course, I did part A, I did part B, and when I got to part C, I realized that I needed to throw out the entire answer key that I had made and start a new one because I misinterpreted the problem. This one is a little confusing. I think ultimately the diagram here can be a little misleading because if you look at the diagram, you see two hanging weights that look to be about the same size. And so I think it could be fairly sort of clear here to look at this diagram and think, well, this object over here, object B, is farther out. That means it has a larger R in the torque equation, and so that should be the one that's generating a larger torque. And this one, because it's pulling down, is going to make the thing rotate clockwise. Now, in most situations, that's not exactly the wrong way to think about it, but they already gave you the information that you needed to answer this question in the problem description. It says here, when the wheel is released, it is found to have an angular acceleration that is directed out of the page or counterclockwise. That's all you need to answer the question. Now, I want to be clear about one thing before we move on, because the Tipper's book does something that I think is a little confusing. Whenever they talk about the direction of angular velocity, angular acceleration, torque, they talk about them being clockwise or counterclockwise. And as I've tried to explain a decent amount throughout this unit, angular velocities, angular accelerations, and torques are either into the page or out of the page. And so it's really important to remember here that when they say, is the wheel going to rotate clockwise, counterclockwise, or none, that's fine. But it's important to realize the angular velocity, which is really what they're asking you about here, is going to either be into the page or out of the page. And so as we mentioned here, the question says, is the wheel going to rotate clockwise, counterclockwise, or none? And the question says, when the wheel is released, it's going to have an angular acceleration that's counterclockwise. So the answer here is pretty straightforward. As stated in the problem description, the wheel is released, which means it starts from rest. If the wheel is found to have an angular acceleration that is directed out of the page or counterclockwise, the wheel is going to rotate counterclockwise and have an angular velocity that is out of the page. It's important to realize here, this rotational motion problem is the rotational analog of a question that says an object has two forces acting on it, one to the left, one to the right. It starts from rest, and when you let the object go, it accelerates to the right. Which way is the object going to go? It's going to go whichever way it's accelerating if it's starting from rest. That's the key idea. I think a lot of this stuff, because they're kind of new situations with this rotational motion stuff, can be a little confusing. If you think about it in terms of everything you already know about linear motion, I think it becomes a lot easier to process, explain, understand, etc., etc. Take a second to pause this video here and write that down. And when you hit play, we'll move on to part B. All right, part B of this question here says, is the direction of the net torque on the pulley wheels clockwise, counterclockwise, or none? How do you know? I'd like you to, again, get a lay of the land here. Take a look at the description, take a look at the diagram, take a look at the answer that we gave to the previous part, and try to answer part B. Come up with an answer, come up with an explanation, and when you hit play, we'll go over it. All right, the answer here is pretty straightforward, I think, if you're thinking about the advice that I gave you just a minute ago, which was to remember everything you know about linear motion. The answer here is counterclockwise. The net torque, since it is the rotational analog of force, causes the angular acceleration, since that's the rotational analog of angular acceleration, they must be in the same direction. The net torque causes the angular acceleration, so they must be in the same direction. That's a typo, I'll just write so here. And since the angular acceleration is out of the page, or counterclockwise, the torque should be out of the page as well. The net force is always in the same direction as the acceleration, and so the net torque is always in the same direction as the angular acceleration. That's pretty straightforward. It's a basic relationship. Remember, I said when we started off this unit, the most important advice I could give you is that the rotational motion stuff, to some degree, is not new. Every rotational quantity has a linear analog, and every rotational concept has a linear analog. And everything that we could say about torque and its relationship to angular acceleration is very similar to everything we could say about force and its relationship to linear acceleration. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And that brings us to part C. Now, as I mentioned here at the top of this problem, once I saw part C and it said, how do the two masses of the two weights compare? I realized, oh, assuming the masses are the same or recognizing that they may not be the same is a key to this problem. And so keep in mind when you're answering this question, we've already been given a lot of information about A, how this wheel is moving, and B, why this wheel is moving the way it's moving. What I'd like you to do for part C here is use that information to come up with an answer to this question. How do the masses of the two weights compare? And when you hit play, we'll go over it. Okay, now the key detail here is figuring out what would happen, I think, if the weights were the same, what might happen if one was heavier than the other. Really try to think about all the possibilities. The main point here, I think, at least as far as the difference between these two weights is concerned, is that there is a different length of the position vector, or R value, in the torque equation. So if we call that RB and we call this one RA, and we remember here that the torque is RF sine theta, it's important to recognize here that the force of gravity is perpendicular to both of these position vectors here. And so we're going to say that the angle is 90 degrees. Of course, the sine of 90 is 1. And so that means the torque is the product of that position vector length and the force. And so clearly you can see here that the position vector length for A is much shorter than the position vector length for B. That much should be obvious to everybody. The key thing you need to recognize to answer this question is which way the disk would rotate if each mass was operating alone. If we take the fingers of our right hand now, applying the right hand rule, and we point them in the direction of RA, that would mean your hand should be pointing to the left of the screen. If we curl our fingers in the direction of the force, which notice here is pointing down, that means your thumb should be pointing out of the page, or counterclockwise. If we do the same for the other mass here, we take the fingers of our right hand and we point them to the right of the screen. If we curl our fingers in the direction of the force, which again acts straight down, then we would find that the torque produced by that weight would be into the page. Notice that makes sense with everything that we've said so far. B would make the wheel rotate clockwise. A would make the wheel rotate counterclockwise. And so now we have a pretty interesting question to ask. What does this information tell you about the masses? Well, we already know that the net torque, because of what they told us about the angular acceleration, is counterclockwise. And so if the net torque is counterclockwise, that tells you that the torque produced by what we'll call mass A here has to be bigger than the torque produced by mass B. And the answer here follows pretty cleanly from that. If the torque produced by A is RA times the weight of A, and the torque produced by B is RB times the weight of B, and we already know that RA is significantly less than RB, then the only logical conclusion we can draw from that is that the weight of these masses must be much larger than the weight of the other masses, because it has to exert that torque with this much smaller r. And so the only way it can generate enough torque to overpower the torque from the other mass and cause this thing to accelerate counterclockwise is if the weights for A here are much bigger. And so as I wrote here, mass A must be larger than mass B. The torque produced by mass A is out of the page, and the torque produced by mass B is into the page. Since the net torque is out of the page, and the distance of mass A away from the rotational axis is smaller, the mass, and thus the weight, must be larger. That's an important thing to realize here. It's the product of only two things. And if the overall product is bigger and the distance is smaller, the weight's gotta be bigger. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And with that, we now get to the last problem in this problem set. It says here in this problem, which is B6QRT09, 3 forces applied to a rectangle torque direction, that we have 3 forces of equal magnitude applied to a 3x2 meter rectangle. Forces F1 and F2 act at 45-degree angles to the vertical, as shown, while F3 acts horizontally. And the question here, asked in all of these parts, is about the direction of the torque. Now, once again, I'd like to bring up what I was talking about in that last problem. The torques involved in this problem are only into the page or out of the page. This book, for whatever reason, describes the torque directions as being clockwise or counterclockwise. It's important to remember here that a torque that is out of the page will cause a counterclockwise rotation, that is positive, and a torque into the page will cause a clockwise rotation. Now, this problem is probably going to be really difficult for us to discuss through the medium of a video, rather than doing this with you all in person. And so really, the point of us taking a look at this problem is to just give you more exposure to the right-hand rule. It was definitely the case in the Zooms last week that people were expressing confusion about the right-hand rule. And so it's something that we should probably talk about. I think a helpful way to think about the direction of torque is that, first of all, you don't need to use the right-hand rule. And you can always identify the direction of the torque by the direction of the rotation. Because if the rotation is counterclockwise, the torque is out of the page. And if the direction is clockwise, the torque is into the page. Another helpful way of thinking about it, which I want to discuss here also, is by looking at the structure of the equation, torque equals RF sine theta. It's important to realize here the fact that the torque is proportional to the sine of the angle tells us the torque is maximized when the angle between R and F is 90 degrees. And so the point here is, if you think about the component of the force that is perpendicular to the position vector R, it will make these kinds of questions a lot easier to answer. Again, as is the case, I'm going to give you the opportunity to try these on your own, and then we'll talk about them. So as you can see here, this question, if you're actually in the worksheet, has a ton of parts. I don't want to do every single part. I just want to look at the few parts that we're going to discuss here in this video. And so I want to start off by talking about A and B. take a shot at answering A and B. Don't go too nuts about the explanations, because at the end of the day, the explanation is always going to be like, well, that's what the right-hand rule tells us, or it caused this kind of rotation. But I want you to go ahead and try A and B, try to apply the right-hand rule, try to figure out which way these things are going to rotate, try to use that to ultimately figure out the real direction of the torque, because those are going to be out of the page or into the page. And when you hit play, we'll go over it. All right, so as I mentioned here, the main objective in trying to figure out exactly how this works is figuring out the direction of the rotation. In these two problems, they are asking us about the torque produced by the force F1, but about two particular points, A and B. What they really mean by the torque about a specific point is if the object was rotating about that axis. If we're thinking about the torque applied to this rectangle here, for example, you can almost imagine when they say, what is the torque about point A, is if this rectangle was free to slide around, like on the table it's on, let's just pretend it's on a table. If you held down this side, this point right here, like if you put your finger right on that red dot that I have drawn there on the screen, if you put your finger right there and then applied F1, which way would it rotate? Then obviously for B, if you put your finger right there, which way would it rotate? Now, an important thing to recognize here is that a really quick and easy way to figure out the direction of the torque has to involve you in drawing, or at least thinking about, that position vector R. And so for B, the R looks like that, as shown there in yellow. That might be kind of hard to see, but I want to definitely differentiate between the colors. And then for A, I'm just going to draw it next to it. Obviously, they overlap, though. For A, it looks like that. So for me, at least, I can only speak personally here, you're going to have to figure out a strategy for this, frankly, that best suits the way you like to think about these. To me, it's already fairly easy to see that this thing is going to rotate clockwise from force 1 because of the way the force is acting. Now, if you don't buy that, of course, there are two ways that you can really figure it out. If you take the fingers of your right hand and you point them down, because that's in the direction of both of the R vectors we have drawn here, your fingers should be pointing this way. And if you take your fingers now pointing down and you curl them this way toward the left of the screen, your thumb should be pointing into the page. And a torque into the page produces a clockwise rotation. Now, if you don't love that way of thinking about it, again, another way of thinking about it is by thinking about the component of this force that is perpendicular to those position vectors, because again, the torque is maximized at 90 degrees, and basically by taking F sine theta, really you're just considering here the force that's acting that way, because notice this component here is opposite of that angle. And so as I drew down here, of course, the component of F1 that acts perpendicular to these R vectors is pointing this way. And hopefully you can tell that if you held your finger on A and pulled this corner of this box this way, it's going to rotate up like this clockwise. And so there's a lot of things that we can say in this explanation here. But the main point is the horizontal component of F1 would make the block rotate clockwise, producing a torque into the page. And of course, I wrote in parentheses, right-hand rule. Now, this may not be the way that you like to think about this. So take a second to pause this video and either write this down or summarize the way that you came up with it in your own writing so you can help yourself to answer this or these kind of questions in the future. And when you hit play, we'll move on to some other parts. Next part we're going to take a look at is part C. Part C here asks if the torque by F1 about point C is clockwise, counterclockwise, or zero. So I'd like you to take a minute to look here at this situation here, really think about how the force is acting, what it's going to make the block do if you held this block down at point C, and when you hit play, we'll go over it. It's very important to remember here that sometimes these diagrams can be a little misleading, the way they're drawn or the way the scale might be shown. And so as I mentioned before, it's really important to draw the position vector r. The position vector r is a vector drawn from the pivot point, or from the rotational axis, essentially, to the point of the application of the force. And so that would be shown like that. And the point is, the torque equation says the torque is equal to Rf sine theta. And what this equation says is no matter how big r is, and no matter how big f is, if the angle between r and f is 0, or in other words, if r and f are parallel, then the torque is going to be 0. And so the answer here is that the torque is 0. Because if you held this block down at point C and pulled on this thing exactly at the corner, the whole block would just slide this way. It would not rotate. And so the basic point here is the force is parallel to the position vector. So there's no torque about that point C. Take a second to pause this video here and write that down, or summarize this in any way that might make sense to you when you look back at this later. And when you hit play, we'll move on. Okay, moving on now, I just want to take a look at two more of these problems on this sheet here, part E and part F, because as you can probably tell, they're asking you about every single possibility, and this thing can get a little redundant. The first part here is asking, and the first part here is part E, is asking about the torque produced by F2 about point B, and then the torque produced by F2 about point C. Again, these are the last ones we're going to do, so take a minute to think carefully about them. Try to come up with an answer, come up with an easy way of understanding it, and when you hit play, we'll go over it. Okay, so in looking at point B, again, it is very helpful to always draw a line from the pivot point to the point of the application of the force. And as you can see here, if you extend that line, these forces are not, or these vectors, I should say, are not quite parallel. And as you can tell here, there's a little bit of room between these two vectors this way. And so ultimately what that means is there is a component of the force that's going to be pushing up this way with respect to that point. And so that means when you push up on the block like this, it's going to rotate counterclockwise. Now, of course, you can use the right-hand rule here, but I think it's a little confusing because you have to take this force vector basically and extend it this way, so where this is the F and this is the R. And so if you take your right hand and you point it in the direction of the position vector, so that would be down this way over here, and then you curl your fingers in the direction of the force, your thumb should be pointing out of the page, telling you that this thing is going to rotate counterclockwise. This one's a little tricky, but once you see more of these, I think you will get the hang of it. Now, before I show you the slide with both of the answers here, let's just go ahead and wrap up part C. If you want to take a look at this again, I suggest you back up the video here because I'm going to talk about part F right now. If we erase everything on the screen and just show for part F, they're asking you for the torque produced by F2 about point C. And notice here, if you start at point C and you draw your position vector, those vectors are parallel. They're in exactly the opposite direction. And so there will be no torque about point C. And so for these questions here I wrote for part E, the forces component perpendicular to the position vector is pointing upward, or at least upward-ish. So the rotation would be counterclockwise. Of course, you can always think about that in terms of the right-hand rule. The thing about the right-hand rule that is confusing, though, as that part demonstrates, I think, is that sometimes you sort of have to redraw the force vector to show the direction it's going in, not necessarily where it's drawn in the diagram. Because remember, when we draw force vectors like in free body diagrams, we usually don't draw them like this. We draw them starting from the object and then going whichever way they're going. And so that's kind of why you have to redraw it here. You say the force is being applied here, and so we draw the arrow that way, ultimately. And then, of course, for F, since the force is parallel to the position vector, the torque produced by that force, F2, about that point, C, is 0. Take a second to pause this video here and write that down or summarize these as best you can in your own words to help you understand this later. And when you hit play, we'll move on. All right, so very quickly before we go here, I want to talk about an idea in the rotational motion unit called Newton's second law of rotation. And in order to understand Newton's second law of rotation, really what you have to think back to is what we said about rotational inertia. So when we first started talking about rotational inertia, we said rotational inertia gets bigger when you have more mass concentrated farther away from the pivot point. And this diagram really best kind of sums up what we have to say about Newton's second law of rotation. You can see here in this top diagram, we have more mass concentrated farther away from the pivot point, and so the rotational inertia is large. Over here, you can see we have mass concentrated not as far away from the pivot point, and so the rotational inertia is small. Now, there are these two circles over here which say spins slow and spins fast. The key thing to remember about what we said about rotational inertia is that rotational inertia is all about an object's resistance to rotational acceleration or angular acceleration. And so the point here is that if you have more rotational inertia, you get a smaller angular acceleration. And if you have less rotational inertia, you get more angular acceleration when you have the same torque. And that ultimately should sound fairly familiar to you, because that basically is everything we said when we were talking about linear motion using the equation F net equals ma. If we have an object with more mass for the same force, it'll have less acceleration. And if it has less mass, then it'll have more acceleration. And so what you'll see here is that Newton's second law of rotation is a direct analog of Newton's second law. We take the rotational analog of the force, we set that equal to the product of the rotational analog for mass times the rotational analog for acceleration. That really already kind of gives away what the equation is, and so I'll just show it here. The equation is the net torque, which is the rotational analog of the net force, is equal to the rotational analog of the mass, which is the rotational inertia, I, times the rotational analog of linear acceleration, which is angular acceleration. Now, of course, that equation is just not made up. Like, we don't just say, well, these are the analogs, so let's just write an equation like that. You can actually derive this equation. And so we'll do that now. You don't have to write this down. I just want to show you where it comes from. We can show here that if we are taking this object and we are applying a force on it, which is tangent to this circle here, so that this object is going to be spinning. So like this object is accelerating and we're holding it with this string here, that we can use Newton's second law to say that F is equal to ma. And if we just show here that, well, it's important to realize the torque is equal to this force times R, right? And as we mentioned when we were talking about these linear rotational translations, the tangential acceleration is equal to R times alpha, that we can basically sub those in. And when we do that, we get ultimately that the torque over the distance, which notice is what we get when we solve that for the force, is equal to m times r times alpha. And here, because we can just move this r over to the other side, when we do that, we get the torque is equal to mr squared times alpha. And if you remember, way back to when we first started talking about rotational inertia, I said the equation for rotational inertia is mr squared, or at least the sum of the mr squareds, but this is only one little object here. So that means its rotational inertia is just going to be mr squared. And so we end up replacing that mr squared with the rotational inertia to get torque equals I alpha. That basic kind of thinking is where that equation comes from. And so let's go ahead and define the terms. Of course, the equation is net torque equals I alpha, where tau is the net torque measured in Newton meters. I is the rotational inertia measured in kilogram meters squared. That's a very important thing to remember. And then the angular acceleration, of course, is alpha measured in radians per second squared. This is going to prove itself to be a very important equation in this unit. So take a second to pause this video here and write this down. And when you hit play, we'll see how we can use this in problems. All right, now before we go ahead and take a look at how we can use this equation to solve problems, I just want to show you very quickly that this equation is in the reference table. And it's important to realize they write it both ways in terms of the sum of the torques, or net torque, exactly like they do for Newton's second law. So if you go up here on the reference table, you will see Newton's second law is written as the sum of the forces over the mass, or net force over mass is equal to the acceleration. And so it's exactly the same thing here. It's a perfectly analogous equation. It all fits in together with everything we said in that regard. Let's go ahead and solve the problem. This problem here is from the rotational motion packet. It's on page 5, number 37. It says a softball player swings a bat, accelerating it from rest to 2.6 revolutions per second in a time of 0.20 seconds. It says to approximate the bat as a 0.90 kilogram uniform rod of a length of 0.95 meters and compute the torque the player applies to one end of it. Okay, so first, let's just write down the list of knowns. We know that this thing is accelerated from rest, so we'll say omega naught equals 0 radians per second to an angular velocity of 2.6 revolutions per second. Remember, everything you need to do here needs to be in radians per second. And so we'll go ahead and convert that. Remember, you just convert that revolutions per second to radians per second by multiplying by 2 pi. And so if you take 2.6 times 2 pi and you round it off to 2 digits here, we're going to get 16 radians per second. We know here that the time it said in the problem was 0.20 seconds. So basically everything is given to 2 significant digits. And they told us here that the mass of this bat was 0.90 kilograms. And we're approximating it as a uniform rod with a length of 0.95 meters. Now, it's very important to ask yourself the question when they say approximated at a uniform rod, like, why are they telling us that? This is really ultimately the first time you're going to see this, and so this would be an important thing to pay attention to. If you look at the rotational inertia reference sheet, you will see a variety of shapes, and one of them is a uniform rod. Actually, 2 of them are uniform rod equations. And so it's important to look at both of these and ask yourself the question, which one of these equations do you think is going to be better to solve for the rotational inertia of a baseball bat? Ultimately, the difference between these two is the axis of rotation. And so the obvious question is, whether you really watch baseball or not, does a baseball bat usually rotate about its center, or does it rotate about the end? Does a baseball player hold the bat in the middle of the bat or at the end? They hold their bat at the end, right? And so that equation, 1/3 ml squared, is going to be the equation we want to use. Notice here, this question was asking us for the torque. And so if we use the equation that we just developed here, I'll just go ahead and write this down in the corner first. Torque equals I alpha, that we don't have yet I or alpha. And so we need to go ahead and solve for those things first. And so that's what we're going to do. We'll solve for alpha first. Alpha, the angular acceleration, is omega final minus omega initial over t. And so that means here the angular acceleration is going to be the final angular velocity, 16 radians per second, minus the initial angular velocity, 0 radians per second, over the time, 0.20 seconds. And when you do that math, plugging in those numbers here, 16 divided by 0.2, you get 80 radians per second squared. So that's our angular acceleration, 80 radians per second squared. Pretty straightforward. Now, as we mentioned, because we are approximating this as a uniform rod rotating about the end, the rotational inertia equation is 1/3 ml squared. And so plugging into this equation here to calculate I, we have 1/3 of its mass, 0.90 kilograms, times the length, 0.95 meters, squared. And when you do that math, you end up obtaining a rotational inertia amount of 0.27 kilogram meters squared. And so now that we have alpha and we have I, we can go ahead and solve for the torque. The torque, as we mentioned in Newton's second law of rotation, is equal to I alpha. And so plugging in those numbers, we have our rotational inertia, 0.27 kilogram meters squared, times our alpha, 80 radians per second squared. And when you do that math, plugging in those numbers here, you get the torque is equal to 21.6 Newton meters. And that's it. It's very important to realize that reference sheet is going to be very, very important for these kind of problems. Because when they tell you the shape of the object, the equation on that sheet is ultimately going to determine its rotational inertia. Another important thing to say before we take a look at the problem I want you to solve here, another important thing to say is once you do a couple of these examples, you will realize that it's much easier to just substitute. And so if you wanted to just solve this equation like this, by just plugging in the equations into Newton's second law of rotation like this, and then just plugging in all the numbers at once and doing the calculation, that is perfectly acceptable. Take a second to pause this video here and write this down. And when you hit play, we'll take a look at the problem I'd like you to solve for your assignment for today. Okay, the problem I'd like you to solve for today is page 16, number 33 in the rotational motion packet. It says here a large grinding wheel in the shape of a solid cylinder of radius 0.330 meters is free to rotate on a frictionless vertical axle. A constant tangential force of 250 newtons applied to its edge causes the wheel to have an angular acceleration of 0.940 radians per second squared. Part A of this question asks, what is the moment of inertia of the wheel? Part B of this question asks, what is the mass of the wheel? And part C says, if the wheel starts from rest, what is its angular velocity after 5 seconds have elapsed, assuming the force is acting during that time? I don't really want you to focus on C. What I want you to do is submit the work for A and B. If you submit C and you know how to do it, that's great. Maybe I'll throw you some bonus points. But I really want you to focus here on A and B. The only thing I want to say about this is that the fact that they tell you this is a tangential force is very important. Because notice here, they are asking you for the moment of inertia, I, which according to Newton's second law of rotation, requires you to already know two values. And you don't know one of those values. And so the fact that the force is tangential is incredibly important. And so what I want you to do here is go ahead, answer A, answer B, write up the solutions, show it on a piece of paper, and submit that. And the first thing in tomorrow's video will be the solution to this question. All right, everybody. Have a good one.